Once again, you're welcome to this channel. Today we have a question. The figure below shows two massless cantilever beams connected by a spring. Stiffness K, which equals 15 meganewton per meter. Assume that the two cantilever beams can be modeled as a linear spring with stiffness KB, that is the stiffness of the beam KB, equals 3EI over L3. That is 3 multiplied by Young modulus multiplied by the moment of inertia I over the length cube, where the E equals, that is the Young modulus, equals 2 times 10 raised to the power 11 Newton per meter square, and the length of the beam equals 0.2 meter, and the I, which is moment of inertia, 10 raised to the power 5 millimeter raised to the power 4. Assume the lower beam tip mass is 200 kilogram. Calculate the natural frequency of the system. Once again, we have to calculate the natural frequency of the system. Now, how do we approach this particular question? First of all, we're given the schematic above here. We're given that the stiffness of the beam of this particular area is connected in series to this. So therefore, how do we calculate the equivalent stiffness when the other part of the beam here is connected in parallel to the equivalent of this particular one? So therefore, by simplifying it, we have our KB here in series with the K. So the stiffness KB is in series with the K, and the two of them are in parallel with KB underneath. So to solve the equivalent using this particular equation, we deduce our K equivalence to be 125 times 10 raised to the power 5 Newton per meter. So by using the formula of natural frequency Wn, which gives us Wn equals the root of Ke equivalent over m. So therefore, our Ke equals 125 calculated at 10 to the power 5 over the mass of the beam tip, which is 200 kilogram. Our calculated Wn equals our calculated Wn equals 250 radian per second. So therefore, our Wn will equals 2 pi f. So therefore, by dividing 250 by 2 pi, we have 39.79 Hertz. So our calculated natural frequency for the whole system equals 39.8 Hertz. Thank you very much for staying tuned.